ladies and gentlemen. Thank you very much, Mr. Chairman, for the nice introduction. In the following 10 to 15 minutes, I'm going to keep you busy with what we are dealing with when we are talking about braided carbon fiber composites, which recently have gained a lot of attention in the industry because it's a very easy and safe way of developing seamless composites having axial rotational symmetry. In terms of manufacturing, we can deal with biaxial braids, which are basically two yarns or pairs of yarns which are intersecting with each other and are being braided along a braided line, or triaxial braids, which are actually equivalent to biaxial, only that we have also an axial yarn added extra to this braid structure. Our aims were to develop, first of all, a model able to provide very quick assessment of elastic properties of these braided structures, which had to be directly implemented in the industry. So some engineers should be able to compute very quickly and get very quickly optimized results of that. And the secondary aim for our research was to develop a model able to completely and correctly identify all the failure mechanisms that are happening in these braided composites. We are halfway with both of them, but successfully halfway. We used all these softwares in terms of programming, and we backed our model up with a set of experimental results. But first, let's talk about the dimensionality of the problem. We had two approaches. One analytical approach, which started at a microscale level. We started developing a model of carbon fibers interacting with matrix, which we extrapolated by mean field homogenization to the behavior of a representative unit cell in that braided material. And as soon as we knew the mechanical properties of that representative unit cell, we could basically determine what's happening in the final braided composite. That was the method that we developed for the industry. It takes about 1 minute to solve. It was written in Mathematica, a bit more details here. So our first step was to describe this representative unit cell geometry in terms of yarn undulation and yarn cross-section geometry. And we used some equations in order to describe these yarn undulation paths. After the undulation paths were taken into account, we needed to know the fiber mechanical elastic properties and the matrix elastic properties, and we could accurately predict the stiffness of that layer of braided material. This approach was further on compared and validated in experiments, in tension and torsional experiments, and it serves as an input for prediction of multi-layer braided filament binding specimens on how will they behave in terms of torsion stiffness. This here is our representative unit cell identified. We took it into account depending on the braid architecture of the planar plain braid or twill braid. We had to divide it, we had to compute yarn paths. In terms of braid architecture, biaxial and triaxial braid, we had to decompose it in several overlapping representative unit cells. For each of them, the stiffness metric was assembled, and then all those stiffness matrices were assembled into a global stiffness matrix. From that on, we could actually take out our elastic constants, and that was the output of the numerical model. That gave relatively good results. I will show you just a slide a bit later when we make the comparison with the experiments, but we were not really satisfied, so we moved into the finite element domain. The previous method was taking 1 minute to solve. This method in finite elements takes about 2 to 3 hours depending on your mesh size. We cut some corners, so we didn't start precisely at the microscale domain. We went somewhere borderline microscale, mesoscale domain. We started with a model of a yarn, modeled as a transverse isotropic material, on which we put Hashim 2D failure criterion. That yarn was further on modeled as a 3D, initially as a 3D geometry in a braided architecture with its neighbors, and the interactions between multiple yarns were taken into account in terms of cohesive contact and cohesive damage. When we move further on towards the multiply behavior modeling, we had to take into account the ply-to-ply interactions, so the interlaminar layer between the plies that were modeled as well with another set of cohesive contacts. In terms of geometry parameters, when we talk about plane grades, the things are very simple. You can fit the cosine model more or less in theory. We can agree that the yarns have a lenticular shape, though there are a lot of current findings that are contradicting each other. So our research was aimed at lenticular shapes. When we talk about twill grades, the situation becomes a bit more complicated because we have these gaps here that are created by another yarn that's coming into place a bit later in time. And we had a couple of functions. In the end, we decided to use a non-continuous function. So we have a region which is constant, followed by half of the cosine, again a constant region, and the other half of the cosine. It turned out to give the best results in terms of the ability of covering the surface with yarns for a given yarn section. In terms of yarn paths, initially it was easy and nice. We had the cylindrical model, which we were able to model a twill and a planar braid and to run our simulations. Our industry partner, which is one of our beneficiaries, said, okay, we need to be able to predict behavior also of rounded corners or rounded structures like this one, what you see on the right side. And we ended up developing the model in Visual Basic for Xenocenics, which takes into account the yarn geometry, yarn path, and whatever grading axis you want to take into account. The final model deals with the following aspects. The yarns are being modeled as shells, having their thickness mapped directly from a 3D solid model developed in zeros. So they don't have they are not shells with constant thickness. And these shells have this Hashim 2D damage initiation model applied up on them. Then, as I said, the yarn-to-yarn interaction within the same layer is being taken care of through means of cohesive contact model. And when we are talking about multiple yarns interacting with each other, so interlaminar failure, we have a secondary cohesive model applied to this. In terms of experiments, what do we actually need to develop this quite complex model? First, we need to know what type of matrix are we using. So we performed tension and compression tests on the matrix in order to determine the tension compression anisotropy and to get our yield stresses and maximum stresses. Then we moved on and we tested unidirectional fibers from the same material as the yarns, and we came up with this fit or this distribution of the material properties, both in experimental terms and through means of Novita-Nakamura homogenization using the Digital software suite. After the experimental tests were performed on the unidirectional fibers, we could fit our Hashim 2D model, which is represented here, and the failure envelopes are on the left, on the right side of the specimen. And that's about it when we are talking about damage initiation. In order to calibrate whatever results we got out of this, we had flat coupons cut from braided rectangular cross-sections. You can braid those rectangular cross-sections. We had flat coupons for both biaxial and triaxial braids, and we compared these results with our numerical prediction as well as torsion tests. When we talk about the ability of the analytical model to predict our experimental results, when we take a look at the biaxial results, everything looks really nice. The areas that you see here are the transversal and longitudinal model lies that the analytical solution predicts having a fiber volume ratio very between 50 and 60%. On the other hand, when we move into triaxial rates, as noted also by our colleagues in the industry, the model tends to overestimate the stiffness obtained experimentally. We are still not sure whether it's our fault from the side of the modeling or it's their fault. Even triaxial specimens have a bit more porosity compared to the biaxial specimens. We are not really sure what happened there exactly. When we talk about the numericals of the finite element model, it's a step forward in understanding the failure of the braided composites, especially the thin wall tubes. We had a lot of discussion whether or not they could actually warp like this. We first developed the model and then we performed the tests. We got this warping in the finite element simulation, and my colleague said it's not possible to think like this. It's not warping, it has to crack. And I told him, yes, if it's thicker, it will crack, but if it's very thin, high chances that it works. In the end, in the test, it turned out that indeed the thin wall tubes failed by warping, and yarn failure, so the interface between yarn fails and they lose structure integrity. The thicker ones fail through the thickness break that goes at 45 degrees. And here are the predictions that we could achieve when we are talking about experimental results versus simulation results. Good agreement with stiffness, good agreement with maximum torque, not that good agreement with the damage endings of the 0.5 and 0.5 torsion. We have some problems in fitting the results, but I hope in the future it will start working better. And to conclude, our future research is aimed at developing a model that is able to predict the evolution, the influence of local effects in both terms of stress, in both terms of strength and lifetime of those braided components. Thank you very much.
Thank you.